Hello dear learners, in this lecture we will continue to understand the plasma properties of geospace. Earlier in our discussions we have seen that we have defined what is geospace and we have understood that the primary state of matter in the geospace is plasma, and it is very important for us to understand the properties of plasma, the electrodynamical properties of plasma. And we realize that the plasma is a quasi-neutral entity in which there are equal number of electrons and ions or equal number of negative and positive charge carriers, and there are also neutral species. Okay, and the fundamental property of plasma is to remain electrically neutral. When this plasma is an external force is applied to displace some charges in the plasma's oscillations will make sure that the plasma as a whole will remain electrically neutral. In the last lecture, we have seen if we displace some charges, some electrons from one point to another point, we have realized the magnitude of the electric fields that would be set up just in order to bring the electrons back to their original positions were very large. These magnitudes were very large, building up enormous amounts of force. Right? And we also seen how the temperature of plasma is always given in the notation of electron volts rather than in kelvins. Right? So we will continue with the same thought experiment in which we will demonstrate how the plasma oscillations will begin and how do we derive a simple expression for the plasma frequency. These properties or these concepts are very basic in plasma physics. If you are curious, you can refer to earlier courses on plasma physics and applications. For the sake of completeness, I am touching upon these concepts in a brief way. Okay. The idea is, so let us consider a plasma to be confined in a slab like this, where there are enough number of negative and positive charge particles. And in totality, there we assume that there are equal number of negative and positive charge particles. We will not look at individual or sub-regions of this space. We will say that this entire region or this entire plasma is electrically neutral. Now, by applying an external force or by any other means, we now displace a small segment of this region such that a small population of electrons are being taken away from this region. Let's say we call this region as, this is region 1, this is region 2, and this is region 3, and let us also call region 4. Now, what we have done is we have taken electrons from this region 2 to region 3. Some electrons are being transferred. What will happen as a result? When there is a surplus of electrons in the region 3, this region becomes negatively charged, and because of the loss of electrons, the ions become the majority charge carriers in the region 2, by which the positive charge will be acquired by the region 2. Now, the electric field is set up in this direction, let us say Ex, because this is assumed to be the x axis or the direction x. Okay. Now, this region 3 is again, region 4 is again electrically neutral, where no force has been applied. Right. Now, the electrons will try to move opposite to the direction of electric field. Because of the electric field Ex, there is a force F is equals to Q Ex. Because of this force, because of the restoring force, the electrons will try to move opposite to the electric field, and they will try to nullify the excessive positive charge in the region 2. But due to the thermal velocity possessed by the electrons, they will always overshoot the initial position and they will go back. Now, the region 1 becomes negatively charged and region 2 is still positively charged. So, it is obvious to expect the electric field to be set up in the opposite direction, making the electrons to move again to region 3. So, these oscillations if they are not damped, if there are not enough number of collisions which will make the electron to lose their kinetic energy or come back to the region 2 immediately, in the situation where there is no damping, these oscillations will continue forever. So there should be a characteristic frequency that should be associated with these oscillations, and this frequency should obviously depend on the number of electrons which are being displaced and any other properties of the plasma. Right. Now, in our discussion today, we will try to derive a simple mathematical expression for this frequency, which we call as the plasma frequency. Plasma. So the plasma frequency or plasma oscillations are the most fundamental oscillations in plasma. Are it's the plasma oscillate to have plasma oscillations is the fundamental behavior of plasma. So whenever plasma is being disturbed, or whenever any external force tries to disrupt the overall charge neutrality of the plasma, these oscillations will come into existence. And this is a simple way to understand the plasma oscillations. So this plasma frequency is the characteristic frequency that is associated with the plasma oscillations. And what is the role of plasma oscillations? Plasma oscillations exist or persist only to maintain the charge neutrality in the plasma. Okay. So for all means, we consider plasma to be electromagnetically active, but it is a neutral entity. Plasma is a neutral entity where the number of positive ions is always equal to the number of electrons or the negative charge carriers. And there are always there are also enough number of neutral particles in the plasma. The physical picture or the thought experiment is simple. Now, the electrons are being pulled and some restoring force is trying to bring them back to their original position. So it is intuitively we can say that this restoring force will of course depend on the amount of charge that is being displaced. So we can say that if it is number of charge carriers, number of charge, amount of charge that is being displaced, so number of charged carriers per unit volume multiplied by the charge. So this gives the magnitude of charge that is being displaced. Charge carriers per unit volume, number per unit volume into charge. This is essentially the charge density, right? So the restoring force, let us call it as restoring force F, is proportional to N times Q. N is the number of charge carriers per unit volume, right? Now, the inertia, what is inertia? Inertia is not allowing these particles to, immediately come and settle into their original positions in the region 2. Right? Inertia is what keeps or what makes these particles move or oscillate. Right? So inertia will obviously depend on the mass, right? This inertia is ultimately what leads to the plasma oscillations. Right? Now, if we combine all these things, electric field is making the particles to the restoring force driven by the electric field is making the particles to come back to their original positions. Of course, that is the driving force. But then, because of the inertia, these particles having picked up a velocity are overshooting their initial positions, right? And immediately a reverse electric field will be set up, and this will decelerate the particles and try to bring them back towards their original position. In the absence of any damping, any loss of energy by the electrons, these oscillations will continue to persist. Right. Now, we can combine all these simple processes in terms of a simple equation of motion, which we write as me d square x by dt square is equals to qe ex. So what is the meaning of this equation? This is the force equals to mass times acceleration. Mass of the particle that is involved here is obviously electron. So me becomes the mass of electron. D square x by dt square is the acceleration experienced by the particle along the x direction, because we have confined ourselves to one-dimensional picture. And this acceleration should be equal to the force that is being acted upon, that the electron is experiencing, which is electric in nature because of Ex. Ex is the electric field that has developed in the x direction, and QE is the charge of electron. So now we can assume that Ex is parallel to the velocity of electron, just to make things simple in nature. Okay. Now, what is our objective? Our objective is to derive an expression for the oscillation of our objective is to derive an expression for the frequency of these oscillations. Okay. Now, where do we start? We have an electric field and we have a force and we have some charge density. We can start by using the Gauss law, which is del dot E is equals to rho by epsilon naught. You can write it in the integral form, integral over a closed surface E dot ds. The surface element is equals to Q by epsilon naught. This expression simply means the total charge enclosed in the closed surface is Q, and the divergence of the electric field is equal to the 1 by epsilon naught times the total charge enclosed in the surface. Okay. Now, let us bring in other variables related to the plasma, which is Ne is going to be equal to the number of charge carriers or number of electrons per meter cube. I am writing it as per unit volume. Okay. And since they are being displaced, x becomes the distance of charge separation. Okay. And there is a surface element we are talking about. Capital A becomes the area of the surface. Okay. The total charge Q is equals to rho times charge density rho times volume. We can write Q as Ne times QE times A times delta Z. Charge per unit volume into charge of one particle times volume. We are just getting the total charge. Okay. Now, let us define our volume or the surface. Okay. Let us say we have a coordinate system like this, which is x, y, and z. This along y, the length is small a, and this is your delta x, and this is your delta z. The area of the surface is capital A. Okay. Now, we are talking about the area element that is here. So, the direction of the area element is perpendicular to the area element at any point on the surface. Okay. All right. So, this is the area of the surface. So, we'll again bring back that integral form of the Gauss's law. Integral E dot ds is integral E ds cos theta equals to Q by epsilon naught, the permittivity of free space. Now, capital A is the area, which is dx dy or delta x delta y. The volume is A times dz, and area of this is A delta z. Okay. So we can write it as integral E dot ds is Ex, since the angle is 180 degrees, Ex times minus 1 small a dz. Or we can substitute what we know. So minus Ex a dz is equals to q by epsilon naught. Q in turn is equals to this, which can be substituted as Ne QE small a x dz divided by epsilon naught. Just substituted this onto the right hand side. And on the left hand side, the value of ds is substituted from here, ds, and angle is substituted as 180 degrees. Cancelling out, we can write Ex, the strength of the magnetic field. Yeah, cancelling out dz, we can write the strength of the electric field as minus x Ne QE. QE is the charge of electron divided by epsilon naught. Now we have, using the Gauss's law, we have been able to get the strength of the electric field that is created in this simple thought experiments. Okay. What does it depend on? It depends on the distance over which charge separation has been created, the number of electrons per unit volume, charge of electron, and the permittivity of free space. Now this expression finds some meaning only when it is substituted into the equation of motion, which is this. Okay. So we can substitute Ex. For the sake of reference, let us call this as equation number 1, and let us say we call this as 2 and 3. So substituting equation number 3 in 1, we can write Me d square x by dt square equals to QE times minus x NEQE by epsilon naught. Or simplifying this, Me d square x by dt square is Ne QE square x divided by epsilon naught, or d square x by dt square plus Q square by epsilon naught Me x is equals to 0. The same equation, F is equals to Ma, but it is written in such a way that the strength of electric field is now known or is represented in terms of something else. Okay, so this equation represents, or sorry, this equation is very similar when we have oscillations in terms of, let's say, in harmonic oscillator, d square x by dt square plus omega p square x is equals to 0. So the oscillations can be expressed with this simple equation. So if you compare these two equations, you will realize that the multiplying factor of displacement in the second term should be in the dimensions of omega p square. What is omega p? Omega p is the characteristic oscillation frequency. So omega p square should be equal to Ne QE square by Me epsilon naught. Okay. Or omega p. The angular frequency is under root NE QE square by ME epsilon naught. This is called as plasma frequency. What is plasma frequency? Plasma frequency is the characteristic parameter associated with fundamental plasma oscillations. Okay. So omega p, just for you to remember easily, we write omega p as n e square by m epsilon naught. Okay. Where n is the number of electrons per unit volume, e is the charge of electron, m is the mass of electron, and epsilon naught. So the oscillation frequency depends on these parameters. Okay. We can also write it as not as angular frequency. We can write it as frequency in hertz, or becomes 1 by 2 pi times n e square by m epsilon naught. So this is a very important parameter to understand the geospace. So geospace being in plasma state, this expression or the value of this plasma frequency changes over the entire ionosphere depending on the ionospheric electron density. Ultimately, this electron density or the variations in the electron density are being exploited for or being used for devising many radio wave communications, etc. Right. Now, what can we say about we can substitute the values of n. N can be anything. N can vary depending on the type of plasma. The mass of electron, we know that it is 9.11 10 to the power of minus 31 kg. Epsilon naught 8.85 10 to the power of minus 12 in units. Okay. So substituting all that, the plasma frequency can be written or can be remembered as 9,000 times square root of Ne in the units of hertz. Okay. So this is the simple mathematical derivation for the plasma frequency. Now, using this plasma frequency, because if you follow some discussion on the basic properties of plasma or why you call a certain gas as plasma, you will realize that the requirement of charge carriers, sufficient charge carriers in the gas is only a necessary condition but not a sufficient condition for a gas to be called as plasma. You can only call it as plasma if it meets certain conditions or certain criteria. These criteria are called as the plasma criteria. So knowing the plasma frequency, we can frame the first plasma criteria, which depends on the balance between the plasma frequency and the characteristic collisional frequency of plasma. Okay, you will expect that the characteristic frequency omega p, which represents the number of oscillations per unit time, and the time scale which is associated with the collisions, mean free time between two successive collisions, you would expect that the mean free time between two successive collisions is much larger than plasma frequency. Only then you call that particular gas with enough number of charged particles as a plasma. Okay, we will not discuss in detail, so we can write the plasma criteria as omega p tau c is much greater than 1. Tau c is the characteristic time between two successive collisions, and omega p is the frequency of plasma oscillations. So if they satisfy this criteria, only then you call that particular gas as a plasma, otherwise you call it as an ionized gas. So not every ionized gas is plasma, but every plasma is an ionized gas. Okay. So in continuation to this, we will, in the next lecture, we will discuss a key concept of plasma physics, which is called as device shielding. We will not derive the entire expression. We will not do the mathematics. Rather, we will try to understand what it is and how it is relevant for understanding the state of matter in the geospace. All right.